Hello everyone. In this lesson, we will introduce Newtonian and non-Newtonian fluids. Through this lesson, you will grasp the characteristics of Newtonian and non-Newtonian fluids, as well as typical polymer melt curves. Based on differences in flow and deformation behavior, fluids are classified as Newtonian or non-Newtonian. A Newtonian fluid is one whose viscosity does not change with the magnitude of shear stress or shear rate, and remains constant throughout. We can see the flow curve of a Newtonian fluid in Figure A. The vertical axis represents shear stress, and the horizontal axis represents shear rate. Since viscosity does not change with shear stress or shear rate, the slope of the line represents the viscosity. The steeper the slope, the higher the viscosity. If we plot a curve of shear rate versus viscosity, as in Figure B, you will find that viscosity does not change with shear rate. Everyday examples like water, glycerol, and dilute polymer solutions are Newtonian fluids. Non-Newtonian fluids, however, are liquids whose viscosity changes with variations in shear stress and shear rate. Their viscosity is not constant. Polymer melts, concentrated solutions, and dispersed systems mentioned in this chapter are all non-Newtonian fluids. The shear rate and shear stress curves for non-Newtonian fluids can be broadly categorized into three types: Bingham plastics, pseudoplastic fluids, and dilatant fluids. A Bingham plastic is a viscoplastic material. This material behaves as a rigid body under low stress, but flows as a viscous fluid under high stress. In other words, when the shear stress is below a certain value, the fluid does not flow. Only when the stress exceeds a specific value does it exhibit Newtonian flow. A typical example is some types of toothpaste. When we squeeze the toothpaste gently and then release, it regains its shape. Only when slightly more force is applied does the toothpaste flow. The reason Bingham plastics exhibit this behavior is that the fluid forms a gel-like structure at rest. When the external force exceeds a critical stress value, this three-dimensional structure is destroyed, leading to a change in viscosity. Slurries, toothpaste, paints, lubricating greases, coatings, sewage sludge, asphalt, and concentrated polymer solutions in good solvents are examples of or closely resemble Bingham plastics. Dilatant fluids are those whose viscosity increases with increasing shear rate, exhibiting shear thickening behavior. Most dilatant fluids are multi-phase mixture systems. They often have a high solid content and poor wetting properties. When shear thickening occurs, new structures often form within the fluid. Let's explain using the dilatant behavior of sand mud as an example. Under normal conditions, irregular sand particles are closely packed, with certain gaps between the particles. These gaps are filled with fluid, which acts as a lubricant. When an external force is applied, the original close-packed structure is disrupted, forming a new structure. The irregular sand particles experience dislocation, causing the voids to enlarge. The system expands. The fluid that originally lubricated the solid particles flows into the lower voids, leaving insufficient fluid above. This makes flow more difficult, and the viscosity increases. Pseudoplastic fluids are those whose viscosity decreases with increasing shear rate, exhibiting shear thinning behavior. Most polymer solutions are pseudoplastic fluids. The reasons for shear thinning can be twofold. On one hand, during flow, polymer molecules orient and align in the direction of flow, reducing viscosity. On the other hand, there is the entanglement between large molecules themselves. When entangled macromolecules are subjected to stress, their entanglement points can be disentangled, thereby reducing viscosity. The flow curve of a typical pseudoplastic fluid is divided into 3 regions. In the range of low shear rates, there is a straight line segment with a slope of 1. This is the first Newtonian region. The viscosity remains largely unchanged with increasing shear rate. This constant, maximum viscosity, is known as the zero shear viscosity. Zero shear viscosity is an important material constant, related to the material's average molecular weight and activation energy for viscous flow. It reflects the material's maximum relaxation time. When the shear rate exceeds a certain critical value, the material's flow properties exhibit shear thinning behavior. At this point, the viscosity of the polymer melt is represented by the apparent viscosity. Here, the intersection point of the tangent line at a point on the curve with the vertical axis resembles the yield point of a plastic fluid. Hence, this is called the pseudoplastic region, or the non-Newtonian flow region. This region is the typical flow regime for polymer material processing. When the shear rate becomes very high, the viscosity tends towards another constant value, known as the infinite shear viscosity. This region is called the second Newtonian region. In practical production, the second Newtonian region for polymer melts is not easily obtained. This is because at high shear rates, polymer melts generate a significant amount of heat, causing the temperature to rise. This alters the flow behavior. Furthermore, at high shear rates, the stability of the melt flow is disrupted, leading to unstable flow. The typical pattern of polymer melt viscosity changing with shear rate can be explained by the chain entanglement theory. It is generally believed that when the molecular weight of a polymer exceeds a certain critical value, polymer chains can form physical cross-linking points between chains, acting like crosslinks. Under the influence of molecular thermal motion, these physical cross-linking points are in a dynamic equilibrium of constant disintegration and reformation. The result is that the entire melt or concentrated solution possesses a transient, cross-linked spatial network structure. First Newtonian region. The shear rate is sufficiently small. The polymer is in a highly entangled quasi-network structure. Flow resistance is high at this point due to the very low shear rate. Although the entangled structure can be partially destroyed, the rate of destruction equals the rate of formation. The viscosity remains constant and at its highest level. It exhibits Newtonian fluid flow behavior. Pseudoplastic region. As the shear rate increases, polymer chains begin to disentangle and orient along the flow direction. As the shear rate increases further, the rate at which the entangled structure is destroyed becomes greater than its rate of formation. Therefore, the viscosity decreases, exhibiting pseudoplastic fluid behavior, that is, shear thinning. Second Newtonian region. As the shear rate continues to increase, reaching a state of intense shear, the entangled structure in the polymer is almost completely destroyed. because the shear rate is very high. New entanglements cannot form quickly enough. The orientation degree also reaches its limit. The relative motion of macromolecules becomes very easy. The system's viscosity reaches a constant minimum value, exhibiting Newtonian fluid flow behavior.